Welcome everyone into the third day of the edition of EVConIndia. I, on behalf of Blue Circle, would like to take a few moments to thank all our esteemed partners for putting their shoulders to the event. A special thanks to our main sponsors, Log9 Materials and Hero Electric, knowledge partner Alvarez and Marcel for creating the white paper, investment partner Indian Angel Network for co-authoring the Startup Ref program, accelerator partner Huddle, and real estate partner GLL. It's been an absolute pleasure working with their teams and getting their valuable support. Also, a big shout out to all my team members for working all the hours to pull this off. Thank you also to our distinguished audience for joining us, most of whom are CEOs, CXOs, and senior leaders. Many of them are our members and are repeat visitors to our webinars. This is very encouraging and motivates us to provide even higher levels of dialogue. For those of you who are new with us today, India-based startup Blue Circle is the world's first sector-specific opportunity and knowledge exchange networking app for business leaders. It is somewhat like the sector-specific LinkedIn for senior leaders, a space to have meaningful conversations, connect with over 15,000 plus rapidly growing community of like-minded leaders from India and across the globe, exchange high-quality curated content, and access business opportunities across 20 sectors, such as e-mobility, energy, real estate, healthcare, and many more. Coming to today's discussion, it is a privilege and a pleasure to welcome Dr. Michael Harenbrock, our distinguished keynote speaker who was handpicked because of the thick input and the rich experience he brings in. In his current role as principal expert electric mobility, he monitors market and technology trends in electrified powertrains and initiates innovation projects to expand the company's product profile based on upcoming technical requirements. He represents MANN+HUMMEL in several clusters, industry organizations, and international task forces working on battery safety. He also acts as a chairman in pre-competitive industry research projects. The discussion will revolve around the topic safer battery packs, an imperative for EV market uptake. Now I request Dr. Michael to please begin the session. Thank you.
Yeah, so thank you very much for the kind introduction and also for giving us the opportunity to share our point on battery safety with the esteemed audience here. So I don't think I have to say too much about myself, as this was perfectly done. Just a few words about MANN+HUMMEL. So because you might not be familiar with the company name, so MANN+HUMMEL is a global leader in filtration. So our mission is to separate the useful from the harmful. So whenever there's any kind of contamination in gas or liquid streams, this is definitely a job for us. It's a company that's family owned, was founded in 1941. We are active in more than 30 countries worldwide, also in India. So we have a good footprint in the northern part of India, but also mainly in the Karnataka state. About 21,500 employees. And those are figures from 2020. And revenue-wise, it was about 3.8 billion euro. Innovation is very important for us. So we hold more than 2,500 patented applications. And we make a lot of filters, so in a highly automated fashion. So that's about 26 filters a second. So if you do the math, you can easily calculate that there were tens of thousands of filters being produced during the course of this webinar. All right, and so let's go now into what MANN+HUMMEL is really active in. So our main business today is in the field of mobility. So mostly products, filter products for internal combustion engines. So like air filters, oil filters, fuel filters, and so on. But we are also on our path in the transformation process towards cleaner air, cleaner water, and especially also cleaner mobility. So this means we are currently exploring how we can make use of our decades of experience in the field of filtration and separation from internal combustion engines and transfer that to hybrid, battery electric, and fuel cell electric applications. And so I don't want to do a sales pitch here. So this is just an overview of some of the products we are doing. So we are very active in the field of balance of plant components for fuel cells, especially in the cathode air path, so cleaning the cathode air. You would find those products on the left-hand side. We are also working on reduction of emissions, which are not coming from the powertrain. So we work on brake dust particle filters, fine dust filters. We are also very successful with smart cabin air filters, so to enhance the level of protection of the passengers inside the cars. Products for e-axles and electric motors are also part of that. But what I will be focusing on today is the products for battery systems and battery electric vehicles. And we also go a way that we want to make sure that the products are not only fit for use in, let's say, passenger car applications, but we always take a look at usability for stationary systems, for example, material handling equipment, especially for fuel cells, buses, trucks, and so on and so on. So these are all base technologies which can then be applied to individual use cases. So, and what's really a very important topic for me, as my colleagues and myself are also monitoring the launch of electric mobility activities in India, and we read a lot about battery fires. And so this is why I want to talk about this today and raise your awareness on about challenges, but also potential solutions. Of course, this can only be a snapshot and one section or one piece of the larger cake. So why is battery safety an issue and becoming a more and more important issue? Customers want to have acceptable electric driving range with one charge. And so you can only achieve that if the energy density on cell level is improving. And I've just adapted a chart here, which was shared by Bloomberg New Energy Finance, showing that from starting from 2010 going to 2020, the energy density of the cells has almost tripled. And you see now with the NMC 811, for example, which is more or less the state of the art at the moment. But of course, the more energy we pack into a certain volume, the higher the risk of malfunction, of course, is. What's very important for all components battery electric is the thermal management. And so it's important that all the components in the different systems used here are always operated in the right temperature window. I think for cabin air, this is absolutely clear. If it gets too hot, this is uncomfortable for passengers. But also electric motors and power electronics need to be operated in an optimal temperature window. But what I would like to stress today is that we also have to keep the battery pack in the right temperature range, and not only during driving, so the charging, but also, the discharging, but also during charging. So this is also one important effect that we have to take care of if we think about keeping battery cells in the right temperature range. So what happens if we go beyond those temperature ranges shown here in green? If we go to low temperatures, which is probably not a big issue in India, during driving, we have less usable capacity of the battery cells, so we cannot drive as far as we could. And charging at low temperatures is even more risky because we would have lithium plating and dendrite formation in the battery cells, which can lead to electric shorts. If we exceed the temperatures, first we see cell aging. So this means that the cells irreversibly lose some of their energy storage capacity, which means that the cells do not enable the original electric driving range anymore. So if you had a vehicle which could go for 400 kilometers in one charge, when you bought it, it might only be 350 or 300 kilometers if we go into high temperatures for the cell aging. And if the temperature gets really even higher, we can go into a thermal runaway, which means that the battery cells can explode and battery fires can build. So to prevent this, you have to apply a holistic battery safety management. And I call that holistic battery safety management because it has to work on different levels. It has to work on cell level, on module level, and on pack level. And there are different elements which can help you to achieve that. So on cell level, of course, you have to understand which cell chemistry you use, and also how this might be more or less critical with regard to certain potential failure mechanisms of the cell. Cell vents are normally included, at least for prismatic and cylindrical cells, but not for pouch cells. The manufacturing quality of battery cells is extremely important. So if you have any, let's say, metal particle impurities in the jelly roll, this is absolutely critical and will definitely lead to some malfunctions. And if you do not have a correct layering of the cells, this is of the different inside the jelly rolls, this is also very, very critical. And of course, what's very important is the battery management system for charging and discharging to make sure that we do not drain too much energy or do not try to put too much energy into cells which are not capable. And this is really one very important topic. And I would really like to make that sure. And this is my main message for today. So there's no 100% safe lithium-ion battery chemistry. Of course, you see here, I've just put some names in here, like the NMC with the high energy density, the LFP, which is becoming a more and more relevant chemistry with less energy capacity, but also lower price, NCA or solid state battery cells. But they all can go into thermal runaway, they can all burn. And so the only thing we can do is to find a good means to reduce the likelihood of those thermal events. And it's also clear the more and more battery cells we produce, the more and more the risk for battery fires will increase. It's just about statistics. But there are very good solutions available which can help us to make our battery packs safer. So on module level, it's normally to try to prevent cell-to-cell propagation of some runaway events. So this is, for example, mica sheets. You can also use aerogel spacers between battery cells, which would reduce the heat propagation from one cell going into some runaway to the next one. And so this helps to contain thermal runaway in battery packs. But on pack level, two topics I would like to address today. A thermal management system, so to make sure that you prevent heat build up in battery cells by removing the heat from the battery cell under standard operating conditions. And the other is emergency degassing. So now let's go into the thermal management section here. As I mentioned, this is on pack level. I mentioned that we need to keep the battery cells in optimum temperature ranges. So what's really stressing the battery cells is on one hand the charging power. So if you want to put a lot of energy into a battery cell in a short period of time, so fast or ultra fast charging, this will create significant heat which needs to be dissipated. On the other hand, if you have large battery packs, it also becomes more difficult to cool them in a homogeneous way, because you want to make sure that you don't have a high temperature spread across the battery pack. So let's say the battery cell at the inlet of the cooling should have more or less the same temperature as the one at the outlet. And so this becomes more and more difficult to achieve if you stay with air cooling, for example. So with the trends to larger battery packs and also higher charging rates, liquid cooling is becoming the state of the art for battery packs, lithium-ion battery packs. So this is just a kind of generic sketch here. The main point is that we have a cooling plate, which is normally a metal plate, where the liquid is flowing through. Then the battery cells are placed on top of those cooling plates, and then the heat will be removed through the battery cell bottom and the cooling plate itself into the liquid. There's a slightly different concept if we are using pouch cells, then we can have the cooling plates also between the pouch cells. What's important is that even if you have a cooling system or liquid cooling system, for example, is to make sure that it also operates properly. So especially if you have particles in the system, this can create severe problems in the cooling system. Of course, it's a closed system, so you could wonder where those particles come from, but they can, for example, stick on surfaces of the different components you make the cooling system from, so cooling plate itself or heat exchangers. And so if those particles are then washed into the system, they can create pump wear, especially if it's mineral or if it's metal particles. But it could also block the cold plate's cooling channels, especially if we are using cooling plates with narrow cooling channels. At the end of the day, this will lead to reduced cooling system efficiency. So what's state of the art for preventing that is to use so-called strainer filters, which would contain fibers or a mesh, which would be placed into the coolant full flow path. It's important to make sure that all the products are optimized for pressure drop, so as little as possible, because you only want to spend as little as possible electrical energy to move the liquid through the system, because you would take this energy from the traction battery. And so the more energy you spend on that, the less energy you have available for electric driving. So this would reduce your electric driving range. So this is why it's so very important. And then, of course, material selection is important. We have to make sure that we don't leach any additives or something like that into the cooling loop here. So this is how these products could look like. So the contaminated liquid would enter here, goes through the through this conus here, and the particles are held back in this mesh structure and are collected here in the support structure. And the clean liquid is then exiting. And here you just see some simulation, pressure drop simulation. We did in this case for a similar design for fuel cell, where we have to deal with very high flow rates. So in this case, it was like 250 liters per minute. We would have at least a factor of 10 less in battery electric vehicles. But this is how those products can look like. Then the second one I wanted to mention is the thermal runaway. And in this case, I would like to focus on emergency degassing. Remember, if the temperature really gets high, we go into this uncontrolled state, which can lead to catastrophic failures and battery fires. So thermal runaway is a very complex process. How it takes place in each and every case really depends on cell chemistry, state of charge, cell type, so cell format, for example. And so this is just an illustrative picture of what's happening. So first you have an cell damage. So this can be nail penetration, can be mechanical failure, can be something like overcharging, overheating. Then the so-called SEI, so solid electrolyte interface, is decomposing. Then we have some reactions between the electrodes and the electrolyte. The separator will decompose. And then as the electrolyte decomposes, we run into an exponential temperature increase. So we have the short circuits, the electrolyte is burning. And then in this second phase, which is fast compared to the first phase we see here, we also have a lot of gas and particle emissions and a lot of heat generations. And of course, this heat can be spread to adjacent cells, which can then initiate a thermal runaway in adjacent cells. And then this is what's called thermal propagation. One additional point, as I mentioned, battery fires are very important. Just want to go back a little bit to the basics. What happens? So how can battery fires take place? So you can call a fire an uncontrolled oxidation of a flammable substance. So you need three elements to create a fire. You need a flammable gas mixture, you need oxygen from ambient air, and you need an ignition source. And so the mix between the flammable gas and the oxygen must be just right. So so that we are in this ignition range. And so if we have, for example, too much oxygen, nothing will happen. If you have too little oxygen, also nothing will happen. And the flammable gas mixture in this case is the mix of gases which are released during the thermal runaway event, for example, through the battery cell vent. The awareness about battery fires is getting more and more important. And so there is new legislation and regulations which indicate that after the first indication of a cell or battery defect shown here, there shall be at least 5 minutes for drivers and passengers to safely exit the car before some runaway occurs. And during this process, you can also have harmful gases getting into the cabin. And so it's very important. So in China, this is already in place, this GB norm here. But of course, on the UN GTR 20 is also dealing with this. And it's expected that these 5 minutes minimum will increase over time. So to make it more and more safe. So at the end of the day, the task is to prevent battery fires and thermal propagation totally. But at the moment, it's about 5 minutes. So units that can help with that are multifunctional venting units. They can help to prevent the risk of battery fires on pack level, as I mentioned. And so those are normally used for pressure balancing for battery packs. And the pressure balancing is required because if you would have a completely sealed battery pack, and you would have different air pressure inside and outside of the system, for example, because of driving uphill or downhill or transportation via airplane, the resulting pressure differences will lead to forces, which can lead to deformation of the battery pack housing or also to leakages. And so what venting unit does, it enables the exchange of air between the environment and the battery pack. So we always have the same pressure levels, but it keeps out particles and liquids. And so those components are also rated according to their IP class or protection class. So this is how those systems can look like. The active component here is the membrane. This is normally mounted. So this is the battery system. This is the environment. And so just remember there's a spike here in the space plate, and I will just explain the function. So if we have a malfunction, so one battery cell starts to vent, the pressure inside the battery pack is increasing. So the membrane is pushed towards the outside and then getting into contact with this pin. And this pin then ruptures the membrane. And so the overpressure, so the gases released from the battery cells can exit the battery pack very fast. So here you see some simulation results. So that's about 100 to 200 milliseconds. And as this component is pretty large, a lot of gas can exit the battery pack very fast. So through this, we can prevent the build-up of significant overpressures in the pack, which could lead to pack explosion. So here we release the overpressure in a controlled manner. But what's then happening, of course, is that all the different gases which are created through the thermal runaway event, like hydrocarbons, CO, CO2, hydrogen, methane, are also ejected. And so now if we don't have, if we have low concentrations of oxygen inside the battery pack, which will often be the case because you would like to put as much battery cells into the pack and have as less free air volume in the pack as possible. Here, outside of the battery pack, those gases start to mix with the ambient air, and thus the concentration of oxygen is also increasing. And so now what's happening is we here have a mixture of flammable gas and oxygen just in the right concentration range, so it can be ignited. And then particles are created during the summer runaway event, for example, by decomposition of the electrodes, or also parts of the battery cell casing, for example, can be ejected. And those can act, and those sparks can act as ignition sources. And so here you can create battery fires outside of the battery pack. And so this is, of course, something you would like to prevent. And so one solution to do this is to add a filter function here, which keeps those hot, and in this case, larger particles from being ejected from the battery pack. And so you more or less reduce, you take the one of the three elements which you need for a fire, so the flammable gas, the oxygen, and the heat source, from the equation. And so this helps you to reduce the risk of battery fires. This can look like this. So you can have some metal grids here, which are of course made of stainless steel to also withstand the high temperatures. And you can add those either towards the inside of the battery pack. And this is of course beneficial because you can already capture the hot particles here. And this is helping you. And not only, and so this is just not just a concept. So we've done that together with a customer over here in Germany. And with this additional hot particle filter solution, he was able to comply with the new GB standard I was mentioning before in China. Without that, it was not possible. So this was more or less an enabler to comply with this new legislation. And so this is just this is why I wanted to share this with you as an additional safety means to be added into the overall holistic battery safety management. So with this, I would like to summarize and conclude. So for electric mobility to really be accepted by the customers, so for fast EV market uptake, the customers must be convinced that the battery technology is safe. And this holds true for all lithium-ion battery technology applications we are seeing, if it's two-wheelers, passenger cars, or trucks. So to do this, it's necessary to reduce and minimize the risk of battery failures and fires. And this can only work if we have a holistic battery safety management on the three levels I was just mentioning. So on the cell level, the module level, and the pack level. And only if the measures we take in those three levels are more or less synchronized and harmonized, we can really reduce the risk. So two solutions which can contribute to that, I've shown you in this presentation. On one hand, for liquid-cooled thermal management systems, to integrate filters, which make sure that you don't have any blocking of cooling channels, and that you don't have pump wear, which would reduce the heat removal efficiency of your system, cooling system. And those multifunctional venting units can also help, on one hand, through fast relief of overpressure. So you prevent the massive build up and explosion afterwards of battery packs. And it can also help you to reduce the risk of battery fires by integrating hot particle filters. So with this, I would like to conclude. So thanks a lot for listening and taking your time with me. And now I would be more than happy to answer any questions you might have. Thank you.
Thank you, Dr. Michael. Very thorough, and I would say narrowed it down to everything. I love the presentation.
Thank you.
I'll move on to the Q&A section. Rajan is asking, how important a role does BMS play in keeping batteries safe from catching fire?
Mm-hmm. So thank you for the question. I think the battery management system is definitely something that's extremely important here, because this is more or less managing how fast you put energy into the cell and how fast you take the energy out of the cell. And so if you want to put too much energy into one cell, which is not capable of taking it anymore, it definitely increases the risk of overcharging, for example, which is one of the sources of a potential cell failure. And so, yes, battery management system is extremely important. I'm not a specialist to talk more about that in detail, but this is absolutely an important element. Also, to integrate safety features. So if you do a monitoring of the voltages of the individual cells or temperatures, that you can more or less shut down individual cells, which are more or less prone to go into some problems afterwards. So very important.
Thank you. The next question is from Aryan. He's asking, sorry, using low quality components is one of the highest causes of battery failures. What are the stakeholders doing to avoid this?
Sorry, I think I didn't get the first words. Sorry, I think I didn't get the first words. Could you please repeat?
Sure, I'll just repeat. Using low quality components is one of the highest causes of battery fires.
Yeah.
So what are the stakeholders doing to avoid this?
Yeah, so what I see is that on one hand, you have to make sure that you can really trust your suppliers. So I would make sure that they comply with the relevant quality management standards and systems. Maybe I would also recommend to do an audit in their facilities. And then I would also use some, let's say, external, either use external test facilities to do some standard tests. So like engineering providers, which are doing this a lot nowadays. So you would have some neutral and independent testing of the battery cells. And then as you gain more and more confidence in that, and the topic becomes more and more important to you, you would also start to build up capabilities in-house. But you would normally go a two-step process. First, collaborate with specialist companies in testing and consulting. And then the second would be to build the capabilities in-house. And just make sure that you don't trust everybody directly, because if somebody is offering stellar performance at very low prices, it would be nice, but I think it's worth to take a second look on that.
Thank you. I'll come on to the next question by Aditi. She's saying abnormal or improper usage is an important reason for battery failure. Mm-hmm. Is it time to broadcast this communication to a wider use base in India and across the globe?
I think there's already, I think this is really a question which depends on how the individual country stays in the uptake of electric mobility. So I think as India is now starting, I think a lot of education will be important. And this is also why I wanted to take this opportunity to talk about that, just to raise the awareness here. I think this should really be enforced by relevant industry organizations and also by the governments, either the local or the national ones. Some of the topics which are now, I'm also into some task forces nowadays, for example, to see how we can warn first and second responders. So what the awareness is there, that it's a new technology. So we have to make sure that people don't think it's plug and play. So you just put it in, but there has to be some awareness that there are risks. This is why I wanted to do the presentation. But of course, those risks can be mitigated. And I think India could definitely learn from the experiences we have made in Germany, for example, or in the US. So there's a kind of toolbox available for solutions. It's just to make sure that you apply those also to the special, let's say, environmental conditions you have in China. In India. So especially with the high temperatures, for example, high humidities. And I think this is where industry organizations and scientific organizations can also play a role.
Thank you. I'll move on to the last question. While you briefly, I would say, you actually touched upon this question. If you just want to share your last remarks. The question is, please share pros and cons of LFP and NMC battery technologies.
Yeah. So thanks for the question. and I think pros and cons for LFP. So LFP has a lower energy density, of course, compared to NMC 811, for example. But what's now being done is that you can put more of those LFP cells into one battery pack. So you have less energy per cell, but more cells. So this helps. On the other hand, of course, LFP cells are less expensive. So it's definitely something you can also use to reduce the cost of a battery electric vehicle. But like I said, it's a trade-off. So you have less electric driving range at lower cost. On the other hand, for NMC, you can maximize your electric driving range. This is something that customers in, for example, Europe are very much interested in. But of course, if they contain more energy, you also have to take more care about or care of the safety issues, potential safety issues I was mentioning before. So what we see nowadays with large OEMs, that they have a kind of two-path strategy. So they would use LFP cells for, let's say, entry-level cars, where customers would also be okay with lower electric driving ranges, and have the NMC more for the larger cars and the more performant cars. So I assume that it will be not an either or, it will be an as well as solution here.
Thank you so much, Dr. Michael. On this note, I would just like to say it's such an insightful and engaging session.
Thank you.
It was a privilege to hear you, and our guests and I have been hooked on till the end, and I've taken home several nuggets. And also, thank you to our leaders in the audience for joining us and for staying till the end and for always asking excellent questions.
Mm-hmm. And maybe one final comment. So if you have any question afterwards, just feel free to reach out to me. So you have my details here on the biz cards. And we could also have some discussions with the Indian colleagues, because I think India is in a very special situation. And it's very difficult to do that from Germany, because you really have to see real life applications of electric mobility. But I definitely support this and keep my fingers crossed. Thank you very much.
Thank you so much, Dr. Michael.
Bye.
Bye.